Okay, thanks so much for the invitation. It's a pleasure to be here, and I wanna. Uh, this talk is about a line of work that I've been involved in what we call network archaeology, and then here's the the long list of my co-authors that will be mentioned during this talk. I'm going to talk about a bunch of papers. Uh, yeah, so you can, since it's recorded, you can go back and check them out. So what is this network archaeology? We are we are this is network archaeology is about statistical problems that appear concerning networks that grow in time. Okay, so you can think about social networks where people come one by one and join the network, or you can think about epidemiology where the infection spreads and becomes larger and larger, rumors spreading, and so on. So there are many instances when there's a growing network, a network grows in time, and when we observe the network today, then we would like to say something about the past of the network. Okay, so the typical questions in epidemiology is who is patient zero, or who started the rumor, or what did the original configuration of the network look like? Okay, so these are the questions that are in this broad area of network archaeology. And we've been trying to give mathematically rigorous results in this area, and trying to understand what is possible and what is not possible in very simple toy models. Okay, so that's what I'm going to tell you about. Okay. So the simplest toy model is involved is uniform and preferential attachment models. So very often complex networks are modeled by really simple random growth dynamics. Okay, that's really simple to describe, but sometimes remarkably they reproduce macroscopic behavior of these large networks. So preferential attachment is, of course, a famous example of that. So in these models, the nodes, the vertices of this network arrive one by one, and every time a new vertex arrives, then it will choose, according to some randomized rule, a node or several nodes to attach to. Okay. So this is how a new when a new agent comes to a social network, he or she will choose some vertices to attach to, and that's how this new agent joins the network. Okay, so really the simplest model is uniform attachment when the attachment is uniformly at random. Okay, so when a new node arrives, then this node or vertex will attach to a uniformly chosen vertex at random, or several vertices. Okay. Um, a little bit more sophisticated model is preferential attachment, where vertices that have a high degree, a high number of connections, are more likely to be attached to. Okay, so this is the famous Albert Barabashi model, and we will also talk about this. So these are the two models that basically that I will mention, and then I will say a few words of what the possible extensions are. Okay, so please feel free to stop me if something is unclear. Okay, so the simplest of the simplest such networks are trees. When every vertex that arrives attaches only to one vertex. Okay, so if we start with a single vertex, then of course cycles will never be formed. The network stays connected. So what we have is a tree. In the uniform attachment model, this is called the uniform random recursive tree, and this tree has been studied even outside of network science a lot. In probabilists understand really well what these trees look like. The same holds for even before preferential attachment trees were invented. Preferential attachment, even before the Albert Barabashi model was invented and became famous, preferential attachment trees had already been studied in probability, and these were called plane-oriented random recursive trees for reasons I'm not going to explain. Okay, so these models are well known and well studied, and all these results come very handy for us in the analysis. Okay, so here's the simplest or most basic of these network archaeology problems. We call this the finding Adam problem. When suppose that you have a uniform or preferential attachment tree that has been grown for a long time, and now today it has n nodes. And the question is that upon observing this tree, but without the vertex labels, of course, we would like to find which one is the root. So who is the first vertex? Who is Adam? Okay. So in what sense is it possible to find Adam, to find the first vertex? Okay. So obviously, Adam and Eve, vertex number 1 and vertex number 2 are completely indistinguishable, right? See, if you don't see the vertex labels, so it's impossible to actually find Adam with high probability. So we have to relax the question a little bit. And the reasonable model is that we would like to construct a so-called confidence set. Okay, so upon observing this tree, this ginormous tree, the statistician is allowed to select a set. So this is let's call it S of epsilon of size k, the k of k vertices, such that the statistician would like to guarantee that the root is in this set with high probability. No? How high? Well, this is the parameter of the problem. Okay, with probably epsilon is the probability of error, and we would like to make sure that that the root is in the set that we choose. Okay, so the obvious question is how large does this k have to be, such that we can confidently say that the root vertex is in the set of vertices that we find. Okay, so how the two parameters of this model are n and epsilon. Okay? So n is the number of vertices, the size of the tree, and epsilon is the probability of error. Okay, let me know if this is unclear. So this is what a uniform attachment tree on 50,000 vertices looks like. So the question is, where is Adam in here? Okay, and how many vertices do we have to pick in order to guarantee that with probability 99%, the root vertex will be among them? Okay, so that's what we would like to understand. Now, this is an older paper with Seb Bubeck and Luc Devroy, and where what we showed, kind of maybe we were surprised that in both models, both uniform and the preferential attachment models, the size of the confidence set is independent of the size of the tree. So what that means that essentially, if I show you this tree of 50,000 vertices, finding Adam in this tree is not easier than if the tree had 50 million vertices. Okay. Another surprise was that finding the root vertex in the preferential attachment tree is strictly and provably harder than in the uniform attachment tree. Okay, and this was kind of surprising to us because we expected that it would be the other way around because preferential attachment trees are famous for having big hubs, vertices of very large degrees that should be easy to identify. Okay, and I will explain why that is not an advantage in this case. Okay. Okay. So how would we how should one go about finding a small confidence set? Well, the first idea that everyone comes up with is just let's look at vertices. Sorry, degrees of the vertices. Okay, because clearly an old vertex has had a longer time to collect more connections. So we expect that older vertices will have a higher degree. And this is true in a sense. For example, in a uniform attachment tree, the expected degree of the root is just, well, Eve will connect to Adam with probability 1, then the next vertex will connect to Adam with probability 1/2, and then 1/3, and so on. So after n steps, the root degree will have about log n degree, and this is concentrated. This is just a sum of independent Bernoulli random variables. There's a center limit theorem. However, it is well known from the theory of uniform random recursive trees that the maximum degree is much higher than ln n. It's actually a constant factor higher. Okay, so just by random fluctuations by chance, there in the uniform attachment tree, there will be vertices that have much higher degree. And in fact, the index of the root, if you order vertices by degrees, then the index of the root goes to infinity. Okay, and there are beautiful, very nice, refined results about degrees in uniform random recursive trees. For example, the papers of Laura Eslava, where she determines of where these high degree vertices are located in the tree. Okay, but in any case, this shows that sorting by degrees doesn't do the job that we would like. You need here the confidence set will have to grow with the size of the tree. Okay, so what can one do? Well, here's the simplest thing that we can do. We look at subtree sizes. Okay, so suppose that we have a candidate vertex here. I don't know if you can see my cursor. Can you see the cursor? Okay. So here's, let's say, here's a vertex, and we can define the so-called Jordan centrality of this vertex by looking at all the sizes of the subtrees that hang off this vertex. Okay, so meaning that if we remove the vertex from the tree, we look the tree will decompose into a forest. So we look at the sizes of the components of the forest, and we say that a vertex is more central if the largest subtree is smaller. Okay, so we can order vertices according to the size of the largest subtree that we order. We get this way. Okay, this is a Jordan centrality. So, for example, if you have a leaf, then there's only one subtree, and that has maximal size. That has size n-1. Every tree has a so-called centroid, that has the property that if you remove it, then all subtrees have size at most n-half. Okay, every tree has one or two such vertices. Okay, those are called the centroids of the tree. But in general, we can just order vertices according to this. And what we proved in this paper is that it suffices to take k, the size of the confidence set, to be about log 1 over epsilon divided by epsilon, and that will work. Okay, so this shows that the size of the confidence set is constant. It only depends on epsilon. It doesn't depend on the size of the tree. Okay, so recently, in a still unpublished paper, we actually could improve this to order 1 over epsilon, and this is interesting because that's the optimum for Jordan centrality. Okay, and why is that optimal? Because you can compute the probability that the root vertex remains a leaf for a long time, and that's about the probability that the root vertex is a leaf after k steps is about 1 over k. Okay, basically this means that nobody will attach to Adam after Eve. Okay, and the probability of that it's a telescoping product. So from this little observation, one can easily prove that the probability of error is at most of the leaves are the least central vertices, so the probability of error is going to be at least 1 over epsilon. So that's the optimum for this particular method. Okay. Also, here from this upper bound, from this new upper bound, we get the expected rank of the root is logarithmic. Okay. All right. So the question is good. So now, if we want optimality, then we should consider what is the dependence on the probability of error. Can we do better than this 1 over epsilon? Okay. So since this is a statistical problem, we can just determine what the optimal estimator is. It's the maximum likelihood estimator. And so what's the maximum likelihood estimator? For every tree, for every vertex of the tree, we can imagine that that vertex is the vertex number 1. And now we can count how many different ways this tree could have been produced, okay? Meaning how many different so-called recursive labelings of this tree there are. So a recursive labeling is just a labeling of the vertices such that along paths going away from the root, all the labels are monotone increasing, okay? And all of these labelings are equally likely. And now we can just count how many there are, okay? And if you count them, then you get this ugly expression, which involves, okay, so let's see what it involves. So this is this is what defines the maximum likelihood, the likelihood of each vertex to be the root. So do I have a picture? Here's a picture. So suppose that we imagine that U is the root, okay? Vertex U is the root. Now, for all other vertices, we have to look at the size of the subtree that looks away from U, okay? So in this case, this green subtree, okay? And we take the product of the sizes of all these subtrees. So for when we compute the centrality or the likelihood of U, for each vertex, we take the size of the subtree that looks away. For a tree, it just contributes as a factor of 1, but for this vertex, it will be 1, 2, 3, 4, 5, yeah, 6 with a factor of 6. So those are these factors, and there's this annoying factor that involves automorphisms of these subtrees that hang off. I won't even explain what that exactly is. Okay, but in any case, we have an expression for the maximum likelihood estimator. Okay, so what can we do with that? First of all, we can prove lower bounds. Okay, so a very simple lower bound that one can get by knowing what the maximum likelihood is that no method can output a confidence set that is smaller than something like e to the square root of log 1 over epsilon. Okay, the constants are not important here. Okay. And the way to prove this is that there are unlikely things that can happen, and one unlikely thing that can happen is that the tree starts out with a long path. Okay, let's say if we grow a tree of size k, then the first 10 log k times it's just a path, and then things go back to normal. Okay? So this is a bad thing that can happen, and only this will make this lower bound necessary. So this is because in this case it's easy to establish that the root is the least likely vertex. Okay. All right. Now we could also give upper bounds by analyzing the maximum likelihood. By just elegantly ignoring this automorphism factor here, which we didn't know what to do about. It's just too complicated. And then we looked at only, this is another centrality measure, and then we look at the product of all the sizes of subtrees that look away from the candidate for being the root. After we wrote this paper, we realized that this notion had actually been defined as a centrality measure by Shah and Zaman, and they called it rumor centrality. Okay, so in a different context, where they were looking at diffusions on regular trees, and there actually also the maximum likelihood was of this form. Okay, and a few years after we published this result, a really surprising, a beautiful result of Crane and Su show that if you order vertices according to rumor centrality, and if you order vertices according to this likelihood measure, then the ordering is exactly the same, no matter what trees we look at. So in fact, these automorphisms factors are not important. So we ignored it we ignored them, but actually it was correct to ignore them. We don't lose anything by doing that. Okay, so now once we have a simpler kind of measure of centrality, then we can analyze it, and what we could prove, this was a little bit technical. What we could prove is that if k is larger than e to the something like e to the log 1 over epsilon over log 1 over epsilon, then that suffices. Okay, so we can order vertices according to Rumor centrality, take this many most central vertices, that set, that will contain the root with probability 1, at least 1 minus epsilon. So this is nice because this is much smaller than 1 over epsilon. This is much smaller than any power of 1 over epsilon. So actually, maximum likelihood performs much better than Jordan centrality, where we saw that 1 over epsilon is not beatable. And also another nice byproduct is that the rank of the root, if we rank vertices according to Rumor centrality, is actually of order 1, as opposed to log n, that was the case for Jordan centrality. Okay, so the optimum ranking is actually remarkably good.
Gabor, can I ask two just clarifying questions?
Of course.
The first one is just a simple clarifying question. So when you say order 1,
it's just a constant.
It's the expectation. Okay, so the epsilon comes from the tails. Okay, all right.
Yes, the epsilon comes from the tails. Yeah, but since the tails here are subpolynomial,
okay,
it's good enough to get.
Got it. And then the previous thing, maybe I just missed it, but earlier you defined this simple measure of centrality where I just take the vertex I'm interested in, I take it out, and then this leads to a bunch of different subtrees.
That's right. That's
but here you're good. Yeah. But now you're defining there's a set capital T in this definition, and it seems like U and V are not even connected. So how am I supposed to think of your Rumor centrality measure, for instance?
So Rumor centrality is so when we compute the centrality of U, you look at all vertices of the tree.
Oh, capital T is just all vertices of the tree.
All vertices of the tree, okay. and you take the size of this subtree, and you just take the product of them. Okay.
Okay.
By the way, instead of the product, you could also take the sum, and that one is called distance centrality because that's equivalent to looking at the sum of the distances. So for every vertex, you look at the sum of the distances of all other vertices, and you call a vertex central if that sum is smallest. Okay, that's called distance centrality. The Rumor centrality is a cousin of that, where instead of taking the sum of the subtree sizes, we take the product of the subtree sizes. Okay. Good.
We also have another question.
Yeah.
Yes.
Gabor, since you're on this, hi, how's it going?
Hi, how are you?
Yeah, thanks. Yeah, nice talk so far. Anyway, so I wanted to ask a question about the observation that this automorphism size doesn't matter. So it's suggestive of some kind of a sufficient statistic kind of framework that because it's, in certain sense, if you have two subtrees that are hanging off that are identical, then there's an orthogonal direction that determines which one comes first. Is that the right intuition?
I think so. Yes.
Okay. Since Ashwin raised this question, I decided to ask it right now. Yeah. Thanks.
Yeah. Thanks. Okay. So summarizing what we proved a few years ago is that the optimal size of the confidence set is between something like e to the square root of log 1 over epsilon and e to the log 1 over epsilon over log 1 over epsilon. And every time I gave a talk about this, I said that obviously the lower bound is strong because we worked so hard on the upper bound, and the lower bound is just trivial. Until this year, when Luigi and his students and postdocs proved that actually the lower bound is the correct one. So if you analyze Rumor centrality more carefully, and for example, in our analysis, we just used a union bond. We didn't take into account the structure of the set of most central vertices. But if you carefully do that, then you can show that actually maximum likelihood does even better. And basically the main obstacle is that silly example that I showed, that if first you have a long path and then things go back to normal. That's really the worst thing that can happen. Okay. There are other ways of really simple, intuitively simple ways of trying to find Adam. One of them that had been suggested before is called, we call it leaf stripping. So let's say we have this big tree. Now we can just remove all the leaves. Yeah. And now we have a new tree, so we can just remove all the leaves again. So like an onion, we keep removing the layers until we have a few vertices. And it would make sense to hope that the root will be somewhere in the core. Okay. And recently we analyzed this, and what we could prove is that actually this works, but not optimally. So if you keep removing these layers until you remove about, well, E log n is the height of a uniform random recursive tree. So we have to stop a little bit before that, but not much before that. Then we will only have a constant number of vertices that depends on epsilon. Epsilon is here, you see. And the size and the resulting, so what remains in the core contains the root with high probability at least 1 minus epsilon, and the size of the little tree that we are left with is only depends on epsilon, but a polynomial of epsilon that we don't really know exactly. So this is it's challenging to actually get the exponent, but we can show that you do need an exponent. So this is you cannot hope for those really strong results that you get for the maximum likelihood. But this really simple method also works. So what happens in preferential attachment? Jordan centrality works in this case, and we proved something that was later improved by Banerjee and Bamidi, who showed that essentially if you take the size of the confidence set to be 1 over epsilon squared, so this is quite a bit higher than the 1 over epsilon that we had for uniform attachment, then Jordan centrality works. Okay, so why is this worse? Well, it's worse because at least the method with Jordan centrality cannot be improved. Because the probability that the root remains a leaf for a long time is much higher than in uniform attachment, right? Because just so at first so Eve attaches to Adam, and if the next guy attaches to Eve, then all of a sudden Adam is less popular. Okay, and then the probability of attaching to Eve now is 1/2. The probability of attaching to Adam is only 1/4. Okay, so after k steps, the probability that Adam is still a leaf is not 1 over k; it's 1 over square root of k. So it's much better, much larger. So Jordan centrality is not gonna work unless the size of the tree is bigger than 1 over epsilon squared. Okay. What about other methods? Well, other methods also cannot do better than 1 over epsilon. Okay. So no method can produce a confidence set whose size is much smaller than 1 over epsilon. And the reason for this is that in a preferential attachment tree, the following can happen with kind of high probability, with probability at least epsilon. So if the tree has size 1 over epsilon squared, then it can happen that the root is still a leaf. And moreover, Eve will have about square root of n neighbors. Okay, and many of them will be leaves. Most of them will actually be leaves. So there will be square root of n vertices that are indistinguishable from each other. So the root doesn't stand out. Okay, so the size of the confidence set has to be square root of n, which in this range of the parameters is just 1 over epsilon. Okay, so this is this is what shows that that in a preferential attachment tree, it is strictly harder to find the root, because in a uniform attachment tree, we know that k can be much smaller than any power of 1 over epsilon, but here 1 over epsilon is necessary. Okay. Now we know, after this beautiful work of Contat, Nicolas Curien, and Lacroix, Lassalle, and Riouard, that in fact constant over epsilon is enough. But for that, they had to look at degrees of vertices. In a preferential attachment, model, high degree vertices are is a good statistic to look at, but not good enough to be optimum. So it is true that the root will be one of the constantly many vertices with highest degree. So by the order sorting by degree will be sufficient to get a confidence set of bounded size. But in order to get the optimal power of epsilon, what they had to look at is pairs of vertices. So you see, it's in some cases, like in this example that I just showed, the root vertex will not have a high degree, but whenever that happens, whenever Adam has a small degree, Eve must have a high degree. Okay, so the statistic that they came up with is looks at pairs of vertices such that the product of the degrees of some function of the degrees is high, and they could prove that that is actually optimal. the set of the size of the confidence set is of the order of 1 over epsilon, which is optimal in this sense. Okay. All right. Let's see how much time I have. So just quickly, instead of looking at only the root vertex, we might want to estimate the entire history of the tree, right? So what we would like to output now is a permutation, is an ordering of the vertices that should be a recursive ordering in the tree, right? So it should be the case that along paths emanating from the vertex that we think the root is should be monotone increasing. So if we have such a permutation, then we can compare it with the true permutation, with the true ordering of the vertices, and we can define the quality of this ordering in many ways. What we looked at is this kind of risk measure, where we look at the index. We look at the index of the assigned index of vertex I, and we compare it with the true index, which is I. Okay, so we look for each vertex. We look at the difference between the true and the estimated arrival time, and then we normalize by this factor where alpha is a parameter. If alpha is 0, then we're just summing up all these differences. But we would like, but it often makes sense to give more weight to early vertices. Those are more important, right? So if alpha is very large, then the root vertex will have a big. If alpha goes to infinity, then this is basically reduces to the finding Adam problem. Okay, so this is written in this paper with Simon Briand, Christophe Giraud, and Deborah Sulan, where we show that, well, first of all, we show a lower bound that no method can perform better than n to the 2 minus alpha. So this risk measure when alpha is at most 2, then no ordering can do better for this risk measure than n to the 2 minus alpha. But you see, if I just take a completely random ordering, then it will have risk at most n plus n to the 2 minus alpha. This is very easy to see. So this shows that that the random ordering will already have the optimal risk if alpha is too small. Okay, so if alpha is 0, or actually if alpha is less than 1, then basically random ordering is the best you can do, at least up to constant factors. And the reason for this is because there are half of the vertices are leaves in a uniform attachment model. In preferential attachment, there are even more leaves. A big linear fraction are leaves, and they are indistinguishable, and there's nothing we can do there, basically, essentially. Okay. But the problem is meaningful when alpha is between 1 and 2. Okay. And what we managed to analyze is what happens if we order vertices by their Jordan centrality. Right? Remember, Jordan centrality is just orders vertices by the largest subtrees, sizes of the largest subtrees. Okay. There have been other, I mean, this kind of problems have been looked at also in applied network science, and leaf stripping methods have been ordered. Also, kind of Bayesian sampling schemes have been, but I think this was the first time when somebody actually rigorously analyzed it, and we could show that Jordan ordering is actually optimal up to a constant factor. Okay, I don't want to talk too much about this. This is not that difficult. Yeah, there are some graphs here that show that actually Jordan ordering is actually much better than ordering by degrees, for example. So the yellow curve here is the optimal ordering, and the blue is the one that we get by Jordan ordering. So it's pretty good. It's optimal in this sense. Here it's optimal up to a constant factor, unlike when we only cared about the root. So everything that I've said so far was about trees, and trees are nice because these centrality measures are quite easy to handle. The Jordan centrality is a very natural one. But as soon as our network is not a tree, Jordan centrality is not even well defined, right? What does it mean that if I remove a vertex, the network may not decompose they may not disconnect at all. So it's not clear how to adapt these methods to more complex networks. Okay? So the simplest possible extension that we could think of was the uniform attachment model, in which when a vertex arrives, it connects not to one parent but k parents. Okay. Okay. The preferential attachment version of this is exactly the Albert Barabashi model, but let's first look at just the uniform attachment model. Okay, so at each time, when a new vertex arrives, it will connect to k independent k randomly chosen vertices. This may be with or without replacement. The difference is not too big. For convenience, we looked at with replacement, sampling with replacement. Okay, so what this means is that there may be vertices that have less than k parents. On the positive side, now the graph is just a union of k uniform random recursive trees on the same vertex set. Okay, because when vertex I arrives, it will connect independently to k previously present vertices. So we just get a union, but of course the problem is difficult because we don't know which edge belongs to which of these uniform random recursive trees. In order to avoid trivialities, we collapse multiple edges, right? So if two vertices attached to, if a vertex attaches the same parent twice, then it will only show us to as one edge. And the question is, can we find the root vertex? Okay. So as I said, the challenge here is that centrality-based methods won't work. Okay. At least the centrality-based methods that worked for trees that we know how to handle don't work. Of course, there are many notions of centralities in networks, but those are not so easy to analyze. At least we haven't been able to get something meaningful. So we have this paper on these type of models. These we call them random recursive tags, and there's another extension of the Albert Barabashi model by Cooper and Fries that also work very similarly in the same kind of framework. So here the idea was that the root vertex. Okay, we know that the root vertex will have somehow a higher degree, but degrees are not enough. But maybe we can look at small subgraphs around the root. Okay, so for example, we expect that the root vertex will participate in more triangles than late-coming vertices. Okay, and this is true, but the statistics, this particular statistic, like counting triangles. Counting how many triangles each vertex is in, is not enough because there will be some random late-coming triangle vertices that can participate in many triangles. Okay, so the next thing we looked at was diamonds. So a cycle of length 4 with one chord in the middle, and there we can show that that late-coming vertices will participate. The expected number of such diamonds for a late-coming vertex will be much less than for the root vertex, but the number of diamonds that the root vertex participates in is not sufficiently concentrated. There is no concentration, so we cannot use that. So we were trying a lot of things, and what ended up working was what we call double cycles, anchored double cycles. So if we have it's a double cycle is just three disjoint paths between two vertices. Okay, so here's 1, 2, 3 of them, and we call the size of these double cycles the sum of these two cycles. The middle path can have length 0, so this is also a double cycle. Okay, and what we could show that counting for each vertex, if we count how many double cycles of a certain size there are, such that the vertex is one of the anchors, then that will work in the following sense. We look at, so there's a parameter m, which we will choose to be something like log 1 over epsilon. Okay, log 1 over epsilon divided by k. Remember, k is just the parameter of this. The k is the number of parents of each vertex. So this is m, and now we look at the size of. We count for each vertex how many double cycles are there, such that the length of both cycles is at most m. Okay, and then we can show that if we choose m this way, then the root vertex will have so we right. So the root vertex will have at least one such side. We will be in one of these double cycles, okay? And the number of vertices that participate in one of these cycles is bounded. It doesn't depend on n. It only depends on k and epsilon in this way, okay? So what this ends up implying is that if we choose k to be this function of epsilon, then we can construct, then there is a confidence set of size k that contains the root vertex with high probability. Okay. Now this is much worse than what we had before, because we have log 1 over epsilon raised to the power of log 1 over epsilon, which is much bigger than any power of 1 over epsilon. So it's really worse. But this is the best we have for this really simple model. So here's a challenge for you. Can you intuitively? I think that that finding the root in this network should actually be even easier than finding the root in a uniform attachment tree. There's somehow more information, even though that information is blurred. But we have the union of k uniform random recursive trees. So I don't know what the answer is, and I don't know how to. Yeah. So that's open. That's a nice little exercise if you're interested. Okay, I'm gonna skip this, and I'm afraid I will have to. We're almost. Time is almost over. Let's see. Let me see if what else can I mention here. Maybe I wanted to. Okay. Yeah. I think I will stop here. I wanted to talk about a different kind of problem that we call the broadcasting problem. Let me just tell you what the problem is, and then, but I won't go into the details. So here the vertices. Let's say we have a uniform attachment tree, but vertices are either Democrat or Republican. Okay. And when a new vertex is born, then it will attach to a random vertex, just like before, but then it will choose a color. And if the parent is a Democrat, then with a higher probability, the new vertex will become a Democrat, but with some probability Q, the vertex is a rebellious vertex and will change party affiliation. Okay. The classification problem is now I show you a tree. So this is how the tree is grown, right? The first vertex here was blue. Second vertex attaches, a good vertex. Third vertex attaches to number 2. It's still a good vertex. But number 4 is a bad child. It's a rebellious one, attached to but changed colors. Okay, and so on. So there are these mutations. The probability of mutation is Q. And now what I show you is this. Okay, I show you the graph with the vertex colors, and my question to you is not where the root vertex is, but what the color of that vertex is. It's just a classification problem. Okay, so I'm asking you, was Adam blue-eyed or brown-eyed? Okay, that's the only thing that we want to know. And there's a more difficult version when I only show you the colors of the leaves. Okay, so all the surviving species we can see what their eye color is, but the dead ones we don't know. Okay, but I still want to know what was the eye color of Adam. Okay, and an obvious lower bound is for the probability of misclassification is Q half, because with probability Q, Eve is rebellious, and then at time 2 we have one blue and one red vertex, and from then on it's a coin toss. We don't know who is what. It's completely symmetric. So with probability Q half, at least Q half is a completely silly and trivial lower bound, but this ends up being essentially optimal. So what we can show is that there is a method, a very simple method, that classifies the color correctly, and the probability of error is at most Q. Okay, so the optimum is between Q, and this Q can be improved a little bit. Sorry, the Q half lower bound can be improved a little bit. We don't know exactly where it is. And the rule is really simple. You pick the centroid of the root, the most central vertex, right? There's a vertex that has the property that if we remove it, then all the component sizes will be at most n half. There's one with high probability that vertex is unique, and we just pick the color of that one, and we can show that is good enough. Okay, and but this only works, of course, if I show you the color of all vertices, right? Because the centroid is by definition not a leaf. If I only show you the leaf vertices, then what we can do is take the centroid of the tree and now look at the nearest leaf, the color of the nearest leaf. And that will give you a probability of error which is still within constant factor of the optimum, okay? Independently of the size of the network. Okay, so sorry for rushing this part. Let me just finish by mentioning a few extensions. We looked at the broadcasting problem in random recursive DAGs. So this extension when there's more than one parent chosen uniformly at random, and we could study the majority rule, but many questions like optimality, what is the optimal rule, is wide open in that setting. A really nice area, open area, is when we give a little bit more structure to these networks. Real networks usually have some kind of underlying geometry. So a natural extension of the uniform random attachment model is the online nearest neighbor tree. So let's say we are in some geometric space. The first vertex is just a point, a randomly chosen point. We pick another point and attach. So when a new point arrives, it attaches to the nearest vertex. So can you do network archaeology in those kind of models? We can talk about more realistic models when there are missing edges, partial information on the vertex order. There are many interesting, practically motivated, interesting questions in this area. What I am very much interested is the question of robustness, because all these models that I told you about are very specific, right? Uniform attachment, preferential attachment, and somehow the methods are often tailored to those. What can we do in a kind of a more robust way? Is there a large set of models in which we can say something, or can we deal with noise? So there's this really nice paper by Crane and Zhu where they introduce a model where what you observe is a tree plus union an Erdős-Rényi random graph. So the tree is sprinkled with random edges, and for preferential attachment, things work out because the high degree vertices can still be seen. For uniform attachment, this is a much bigger challenge. Okay, I think that's all I had time to tell you.
Thank you very much. Great talk.
Thanks.
So the way we'll structure this is we'll take any questions now. So feel free to unmute yourself and ask any questions. And this is basically going to be an open Q&A for 5 minutes. And then if there are questions after as well, we just stick around. So we sort of structure the questions into two. Yes, Venkat.
So, I mean, in the spirit of generalizations, I was trying to think of what might be an interesting generalization. And I was thinking, one thing that might be interesting is to view this line of work as a way of providing some kind of a diagnostic for an ambient graph of some sort. I don't know if that's something anybody has worked on. So So you have maybe a family of connected graphs, and this tree formation is happening within the class of spanning trees of that graph somehow.
Yeah.
It seems like some of the same techniques might go through, and you might end up getting something that helps you to understand some property of that graph or something. Is that something people have pursued? It seems natural to me.
So a very natural one. I very briefly mentioned this diffusion on trees that people have looked at. So you have an infinite, let's say infinite ternary tree, and you put Adam at some vertex, and now the disease spreads, randomly to neighboring vertices, and then so now you have a tree, and you want to find the root of it.
Yeah, but that's, I mean, the ambient object is already well defined in some
It's
sense.
already well defined.
Yeah.
Okay.
So just thinking, maybe, there's some limit. Maybe, you could have a family of Reddish-Rennie graphs within which these trees are being formed, or
That's
something
right.
in the local weak limit regime, or some such thing, or some graphon type
Yes.
picture. And you might sort of discover some diagnostic through this process. Yeah. And you seem to have a lot of technique already built up. So, it seems kind of interesting. Yeah.
So another thing that would be a different talk that we've been thinking about, we call those temporal graphs. So let's say you have an Erdős-Rényi random graph that represents when people meet, right? So two vertices are connected when they met. But if you want to model the disease of an epidemic, then the time when they meet is also important, okay? Because if we meet before any of us is infected, then nothing will happen. So the disease so now we take a random permutation of the edges, and those are the times when these meetings occur, and now we look at temporal paths. Okay, so temporal paths is just a path with monotonically increasing edge labels. So this defines so now the disease spreads on what this is called the foremost tree from a vertex, and then you can ask exactly the same kind of questions. So that's something that sounds like what you're suggesting.
It's sort of related. Okay, thank you.
Yeah.
Any other questions from the audience? Again, please feel free to unmute and ask. Or if you are shy, please put it in the chat and I'll ask. So I have one question that's maybe more in technical territory, but so one maybe surprising thing was that when you define this generalization to the uniform K case, the algorithms didn't strike me as recovering the K equals 1 case. For the tree itself, right? Like, so is there
it's completely orthogonal. It bothers me too.
So is there a natural interpolation somehow? But like, even if we did K equals 2 is the best thing you know how to do your algorithm for K equals 2. I see.
Yes.
Okay.
Yes.
So this is
and it really shouldn't be. It really shouldn't be. There should be something nice. You can look at distance centrality or eigenvector centrality. But those are much harder to analyze than, because basically I didn't say this, but a lot of this analysis is based on polyarn models, because these subtrees, they behave as polyarn, right? If you have a uniform attachment, even preferential attachment model, the probability of attaching to a certain subtree that's proportional to size. So that's exactly like a polyarn. So we use a lot of those techniques. If you don't have that, then the maths becomes much harder.
Hi. I have just one question related to this list here. So the geometric models here, like, what is the interesting problem here? Like, it's just every node has a random geometric embeddings and connect to the nearest neighbor. So, like, what kind of problem is interesting along this line? I'm just curious.
Okay, so I should have added, there's a recent paper by Elhanan Mossel, I think Magdus Sudan and Anna Brandenberger, who look at finding Adam in an online nearest neighbor tree. Okay, but they could not really just solve the problem when I show you the combinatorial tree, and I'm asking you where the root is. But if they in their version, the tree comes with labeled with distances, so the edge lengths give you come with the distances in that case. So here it would be nice. What can we do if there's kind of an unknown underlying geometry, right? So we don't know anything about how these connections occurred. We just observe the combinatorial graph. Can we still find the root in the same vein? Yeah. So instead of looking at the uniform recursive tree, look at the online nearest neighbor tree, for example, that has a root. Can we find it? That would be
But yeah, but I don't know. I need to think more, because I think if it's a K-DAG, as you show, like it makes more sense. You have more cycles, right, locally, because of geometry. But like,
yes.
But if you don't have any information, just this tree, I don't know what you can learn from the tree, right?
Well, you can, because these trees do have some kind of a typical behavior.
That's
a lot of that is studied in this paper. It's a big paper by Lichev and Mitche. But yeah, I agree. I agree. It's not a very easy problem.
Okay. Thanks for the answer. Yeah.
Any other questions from anyone else? Again, this can be the formal time at which the recording ends. So if you want to ask any questions that will not be recorded, you can